Alright, so what I want to talk about in this video is some of the implications of Green's theorem and some cases in which Green's theorem does not apply. So the first thing I want to talk about is the case when the vector field f is conservative. So we know that if f is conservative, it usually implies that we can the cross derivatives of its components are going to be equal to each other, and this is something that we discussed already when we talk about conservative vector fields. And if this is the case, then Green's theorem is telling us that the double integral here is just going to be 0, because you're just going to be integrating 0 here. And then this implies that the line integral over that closed contour C is also going to be 0. So this is a pretty big implication, and it essentially means that if you have a closed contour, doesn't matter what the shape is, as long as f is conservative, that means that f of x differentiated with y and f of y differentiated with respect to x are equal to each other, then you're going to have the line integral along that closed contour is going to be equal to 0. Now, why is that the case? Well, in order to understand why this is the case, we need to explore another integral theorem called Stokes' theorem. Now, this is a theorem that essentially relates a line integral of a vector field to the curl of a vector field on a surface integral. We haven't really done surface integrals yet, but I'm going to give you a little bit of a run through it, and then we're going to explore this a little bit later on in the series. So the idea is that if you have a surface, you're going to have a unit normal that is pointing normal to that surface, basically, along some element ds. So this is an infinitesimal element of the surface, and it is a vector quantity because it has an orientation. Now we can decompose that infinitesimal surface into the following expression. So this should actually not be a vector. If we take the total element of surface, multiply it by some unit normal vector that is pointing in the direction of that vector, then we can rewrite Stokes' theorem as follows. We can write the curl over some surface S. This is going to be nabla cross F. So this is the curl of F cross N. So that's just the unit normal vector times the element ds, which is just going to be the total surface area along which we're going to integrate that. Now we know that if f is conservative, it implies that the curl is going to be equal to 0. So by Stokes' theorem, we already know that this whole thing is just going to be 0. So it essentially also implies that the line integral is going to be equal to 0. So not only is Green's theorem telling us that this is 0 when f is conservative, but also Stokes' theorem is telling us that as well. Now, why is that the case? Well, it so happens that Green's theorem can actually be thought of as a special case of Stokes' theorem. So what we're going to do is we're going to imagine that we're going to confine the region of integration, or the region D, to just the xy plane. So we have a curve that only exists on the xy plane. It is a closed contour. And now the surface here that we're going to integrate is essentially, it has a unit normal vector that is always pointing along the z direction. So in this particular case, what we have is a unit normal vector, n, that is going to point upwards along the z-axis. So it is going to have this. And then if we take the curl of f, and imagine that f is just confined, well, it is essentially just going, it doesn't matter if f is a vector field in 3 variables, it is essentially just going to be the following. We have I, j, k. This is derivative of x with then y, then z, and then fx, fy, fz. Now, what we know that we're going to have is the following. We're going to have I times some components. We're going to have y fz minus z fy minus j x fz minus y fx. Actually, this should be partial with respect to z here. And then finally, we're going to have k is going to be equal to x fy minus y fx. Now what's going to happen is when you multiply this curl, when you take the dot product with that unit vector, what's going to happen is this element and that element are going to become 0 because you're going to be multiplying them by 0. But here, you're going to have this element multiplied by 1, so this one remains intact. So in the end, what you're going to get, because the dot product is a scalar quantity, you're going to get the following expression. Which we know, if we just write it in the same way we have been writing it all along, it's just going to be this quantity. And what does this quantity remind you of? Well, it turns out that this is the same quantity that we use in the double integral for Green's theorem. So we just showed that you can actually derive Green's theorem from Stokes' theorem, which is a more general integral theorem. And then what happens is now you're going to have the original integral, which was this right here. So we have a double integral with respect to a surface S, the curl of the vector field dot product with ds, in which ds is oriented along some normal vector. Then this is going to be equal to the same region S, and now we're going to have this here minus fx over y times the element of area ds. But in this case, the surface area is essentially just an area that is flat. So in essence, this is the same as just saying some area A, so dA. And this is the same as saying, well, some region D, because it is essentially going to be the same region. So this is how you get Green's theorem from Stokes' theorem. Now, what is the implication of that? Well, Stokes' theorem will tell you that if f is a conservative field, then this line integral would be immediately 0. Whereas and in fact, I think this should pretty much be generalized. This should actually be a closed contour, because otherwise it doesn't make sense. This needs to be a closed contour because we need to have a specific area upon which we're basically integrating the vector field. So if I have a closed contour, then if the vector field f is conservative, which means that its curl is 0, then Stokes' theorem tells you that the line integral of the closed contour is going to be 0. And as a result, Green's theorem is going to tell you the same thing, because Green's theorem is derived from Stokes' theorem. So it's like a special case of it. So this is a really important thing, because if we can prove that f is conservative, then we don't even need to evaluate the line integral at all. We know it's going to be 0. Now, another implication of Green's theorem, well, it's not really an implication, but rather just a continuation of what we just found, is that if you have two curves, so let's say this is C1, and then this is another curve C2, and then the region D is just the region that is enclosed between those two curves, then Green's theorem tells you that you can easily find, so we're going to have C of, say, some vector dr here. This is going to be equal to the sum of those two, so you're going to have C1 of the vector field dot product with dr plus C2f dot product with dr, and then all of this is still going to be equal to d, and then you have f of y over x minus f of x over y dA. So essentially, you still have this relation, so it doesn't matter if you have two curves like that, you can still apply Green's theorem. The only problem with Green's theorem is that it always falls apart for when you have singularities contained within the region D. So by a singularity, I essentially mean something like this. Imagine that you have a function like minus y over x squared plus y squared. Now, why is this function a problem? Well, this function is a problem because at the point 0, so if you have your x and y plane here, when x is equal to 0 and y is equal to 0, so essentially just the origin, then this thing is going to become infinity, so you have a singularity at this point. So in essence, if you define a region that somehow encloses that singularity there, then you can no longer apply Green's theorem to evaluate the line integral of that C. You're going to have to evaluate it in the normal sense. So this is a special case in which Green's theorem would simply not work. You wouldn't be able to formulate the problem in this particular form because you have a singularity or an undefined value contained within that region D. Otherwise, if for example the region was defined outside of the singularity, then you could easily just apply Green's theorem again. So this is a special case in which you need to be careful. So in essence, any points in which you have undefined values or just infinity or things just exploding altogether, you cannot use Green's theorem. Otherwise, you can apply it as long as you have a simply connected region. So this is a point that I should have brought a little bit earlier. A simply connected region or a Jordan curve is simply a curve that is closed, but it does not intersect itself at any other point. So basically, if a curve went around like this, it is a self-intersecting curve, which means that it is non-Jordan, and in that case, you cannot apply Green's theorem because you have a little bit of a problem there. So there are some conditions that limit the usage of Green's theorem, but as long as we can identify those things and we know that there are no problems with the region of integration, we can easily apply to simplify things for us quite a lot.